What's up, everybody? This is Matt Brown with another IoT hacking video. Today we are going to dive into the world of 4G LTE and how we can, in our lab environment, in a sanctioned way, perform testing and set up a cell network, a base station that we can connect client IoT devices to that speak over 4G to backend internet systems. And so we are going to go over to the workbench and check out my setup, and then we're going to do a quick demo. And this is going to be the first of many videos. So if you are new here, definitely hit that subscribe button because I just love to share this kind of educational content with you and the community. So let's jump right into it. And before we go over to the desk, I just want to give a little bit of a primer to the world of 4G LTE. So we're going to actually scroll through this website just a little bit, and I'm going to leave links to this awesome free resource down in the description of this video. But we're just going to go over some of the terminology because, man, in the world of wireless architecture, there is a lot of acronyms. They love acronyms more than anyone else, and I remember in my master's program, I actually took a class, whole semester on wireless architecture, and for our final exam, they let you have like one sheet of notes, and the entire paper was just full of acronyms. So we're only going to go over a few of them today, and some of the basic components of a 4G LTE setup. And so some really core acronyms that you're going to want to know in the world of LTE. So first of all, we have an evolved node B, or what it's really referred to as an E node B. And this is the base station. This is the cell phone tower that is transmitting radio to cell phones, to user devices, right? And then those user devices, we refer to those as user equipment. And you will see the UE acronym refer to those client devices that connect up to a cell phone tower using RF. And then there's the back-end data center systems that are typically involved. They're typically, multiple systems inside of a very complex data center in the real world. But we just kind of call all of those systems an EPC, an Evolved Packet Core. And this is going to manage a bunch of things like, routing of calls, authenticating user equipment to the network, and all of that fun stuff. So those really are the three core components, and we're going to see all those today in our demo. And so again, this website talks a lot about a lot of cool stuff about frequencies, about bands, about LTE channels, and so you can avail yourself of this resource. Definitely check it out because it's going to explain some of the stuff in the software we're going to go through today. And so, but before we jump into the software, I want to go over to the workbench, and we're going to look at my lab setup. So over here, we have got a couple of things going on the workbench. So first of all, I've got my software-defined radio. Now, this is a bit of a higher-end radio, and unfortunately, if you really want to get into the world of LTE, you are going to need a bit of a higher-end software-defined radio. So this is a USRP. You can do this with a Lime SDR or a Blade RF. Those are a little bit cheaper options than this, but honestly, I've been given advice by people who are better at software-defined radio than me, and they say you kind of get what you pay for. So that's why I went with the USRP. And then you will notice that we are connected to our user equipment right here that is rigged up to a Raspberry Pi. So it would be against the law for me to transmit this base station signal if this were not inside of an RF enclosure. And so I currently don't have an RF enclosure, so this is the method that I go with so that I am not emanating RF. And so you'll see that we have a couple of attenuators that reduce the power of the signal going in between our software-defined radio and our cell modem right here. And so, yeah, we got, SMA, and then we got UFL, and then we are plugged into the main antenna over here on our cell modem. And so you'll notice that I've got this like antenna that usually goes on this modem for connecting to like a real cell phone tower out in the world, and I've disconnected the main LTE antenna, and we have plugged in the one that's connected up to our software-defined radio. This other one over here is a diversity antenna. It is a secondary LTE antenna, and in my setup, I disable this in software, and we might go over that in a different video, but that's going to be out of scope of this video. And the other antenna is just a GPS antenna, so we can leave that connected. That's just fine. That's just for receiving GPS. So you'll notice that that is connected via USB to my Raspberry Pi. So the Raspberry Pi is going to be acting as our user equipment, our client device that is going to connect to the cell network hosted on our software-defined radio. And so, yeah, you're probably going to say like, yeah, okay, you don't need to connect it via USB. This is actually a Raspberry Pi hat that you can plug into the Raspberry Pi, but I have this kind of cool case and it doesn't fit without a riser, and so I just connect it up via USB like that. And then the one other thing that we're also going to leave out of scope for this video, but I just want to mention, is that the way that this operates is that right inside of here we have a SIM card that we have already programmed with a smart card reader writer like this, and there's a couple different SIM card options. I highly suggest using these SIMOCOM SIM cards because they work a lot better with open source software than these cheap Geiler cards. So these you can get on Amazon, super cheap. These you got to get from Germany, from those guys over in Germany, but they make very good SIM cards. They work with the open source software. We're going to talk about that in another video, all of how to use this device to program these SIM cards in order to be able to authenticate and talk to our cell network. But we'll leave that to another video. But that's our setup. This is going to act as the cell tower. Obviously there's, this is plugged into my computer, and there's going to be a bunch of software running on the Linux side. And, attenuators reduce the signal power, and that's connected up to LTE on our modem, which has a SIM card, which will authenticate to the base station. And then this will run software in order to get an IP on our LTE network. So that's a lot of moving parts, a lot of stuff going on over there. And if you are not familiar with this awesome project that we're going to be using, this is SRS RAN 4G. It is an open source software project that has been around for a while, and it allows us to spin up using a software-defined radio like our USRP. Like I mentioned, there are some other ones that are supported, but we're just going to be talking about things from the USRP perspective. It allows us to spin up let's go back to our documentation here. So it implements an eNode B. So the eNode B is the thing that transmits RF. It transmits radio, right? Out using a software-defined radio. And so it's going to implement the LTE wireless protocol, right? And it additionally implements the EPC, all of the back-end software that stores the critical elements that are in the SIM card, and so that they can mutually authenticate and talk to each other. And we're also going to talk about that in another video when we talk about SIM cards, but LTE does mutual authentication with symmetric keys. There are these two keys that you program into your SIM cards, and we'll look at those in a little bit, but they perform symmetric encryption, mutual authentication. So when a cell phone, when a piece of user equipment connects to the eNode B and to the cell tower, it is authenticating that the cell phone tower is legit, and that the cell phone tower has those keys in its possession. There's a proof algorithm that takes place. And then obviously the cell phone tower is additionally authenticating that the user equipment is valid, right? Has those keys as well. So let's jump into our software, our SRS RAN software that we are going to run. And so we're going to be running in 2 different terminal windows for those 2 different software components, right? The one is the radio component and the other is the backend component. So that's what we're going to be doing over here. So let's use a little bit bigger. Nice. Okay, so up top here, we are going to go and take a look at our EPC. So this is the software backend. And then over here, we will look at the configuration for the ENB, the eNode B, the radio component. So right here, we have the config file that operates on kind of the backend software system for the LTE network. And we're not going to go over all these configs, but we're going to hit the highlights, okay? So here we have 2 values, the MCC and the MNC. So these things, so MCC stands for mobile country code. Got to remember all my acronyms here. Mobile country code, and MNC is mobile network code. Basically, it identifies the country and then the network, like AT&T, Verizon, etc., that the cell that is operating is associated with, right? And so obviously the networks are like different companies and things like that. Now, these values here that we have in our config file are actually reserved for testing purposes. And so there is no country. Like if you look in the specification, like 001 and 01, it just says test or testing for these values. And so we're going to use those just in case we did happen to emanate a signal out into the world that we would have very few devices wanting to try to connect to our cell, even though we are not emanating signals, because that would be a big problem and we don't want to have the FCC knocking on our door. So we have some other things like this bind address, and this is basically where the different components in the cell software system, in the SRS RAN software system, are going to like bind which interface. So it's going to bind on loop back here. The APN, this is a critical value. So an APN is the like the name of the network that you are on. And so APNs, there are public and there are private networks that you can operate on. Like, so your cell phone, you have internet on your cell phone, 4G LTE, and you hop on like I got Verizon, right? You hop on Verizon and you get an IP address and you can start, sending data out to the internet. That is a public APN. There are also IoT devices that operate on private APNs, and private APNs are basically a deal that they have ahead of time with the cell provider. And that cell provider sets up a VPN effectively back into some internal network of theirs, or it just egresses out of a known IP that they whitelist, right? And so the API services that those IoT devices communicate with are not publicly accessible, but they're only accessible through that private cell network. And so that is, there's different kinds, right? But the name of our APN here we're going to be hosting is NMAT. It's going to be the name of our private network. So, and then DNS is just the DNS server that's going to hand out. We don't need to go over all of these. There's some encryption, stuff. And here is the HSS. So this whole backend system, in reality, like in a real cell phone network, these would be multiple different microservices or servers inside of a data center that would be operating these different components. If you remember, a while back, there was a story about the NSA compromising some telecom companies overseas The things they were going after was the HSS. And that's because that's where the keys to the kingdom are stored. Remember I said it's a symmetric encryption that takes place. There are these keys that get programmed into SIM cards and put on the SIM card side in user equipment. And then there's also a master database where all of those keys are stored. And that's the HSS. And in this system, it's very, very simple. It's a CSV file. And we're going to look at that in a minute. I'm going to show you what the keys are to my private network. So if you come and physically plug into my SDR, you'll be able to perform a man-in-the-middle attack on me. All right. And then there's some other values here about the gateway. So this is basically the interface where the traffic is going to egress out of our network into the rest of the world here. So this is actually the interface. We're going to listen using Wireshark to be able to see the packets as they exit the LTE network and go out to the plain old internet. And then there's also some logging functionality. Now let's go ahead and take a look at the eNode B, the radio component of our cell here. So here we go. We've got our ENB config, and we have a repeat of those MCC and MNC values. You're going to want those to be in sync across these two different config files within SRS RAN. We've got some other stuff. I'm going to skip to the stuff that matters here. I'm going to skip down to the RF configurations. So we have the device arguments, and this is specific to my USRP. I have a USRP type B200. It's actually the B205, but whatever. It's that class of USRP device, and so there's some configuration there. If you're using a Blade RF or a Lime SDR, you're probably going to have to change that setting. And then the other really important thing that when I was getting this specific testing setup to work are these TX gain and RX gain values. And so so I had this TX gain set higher at first, and I was having a bunch of connection problems. And the reason for that is really interesting. So I'm gonna point at my setup over here because this is an easier way to explain it. So when this side, so when the cell phone tower side transmits more powerfully, and it goes over to this device, then this device reads that high power signal, and what it perceives is that it thinks, oh, I'm really close to the cell phone tower. If I'm really close to the cell phone tower, I don't need to transmit with a lot of power because I can save battery. I can save power that way if I don't transmit as much. And so it transmits a very weak signal, and then of course that comes through these attenuators and gets even weaker when it hits our system there, and it was causing all sorts of connection problems. And I'm like, oh, okay, like I actually have to transmit less so that the user equipment will transmit with enough power on its end. So that's kind of some things that just a little bit of Googling or ask your favorite LLM for some advice on configuring these, and eventually you'll figure it out. So and then there's just some logging stuff. But let's go. Let's get this running. So that was a lot of explanation, and I'm going to just hit up arrows until I get to my start stuff here. So the first thing I'm going to do is I'm going to start the EPC, that software backend to the LTE system. And so that's going to just spin up a bunch of stuff. And then what we're going to do, oh man, I'm getting ahead of myself here. So just kidding. We're going to look, we need to look. I need to dox my keys here, all right? So this is the user database file. So right here, what you will see is you will see the IMSI value, the like ID number of my SIM card, and then two very, very critical components here. You will see the key, which is also referred to as the KI. So that you'll see that sometimes. This is a key value, and then this OPC value, which is another key. We're not going to go into how the authentication is calculated, how the mutual authentication is done, but for an attacker to emulate or for authentication to be performed, you need both of these keys. Both of these keys are effectively secrets that are, again, programmed into the SIM card. We're going to go over that in a different video. And they're stored on this back end so that the user equipment and the eNodeB will authenticate to each other. So let's go ahead and start that up again. Sorry about that. And then we're going to fire up our eNodeB, and I've just got a part of my script that like catches it. I'm basically just wrapping around the tools, and it just says remember to connect your attenuators. So we do that, and now we are broadcasting our cell network. And oh gosh, my Raspberry Pi was like already set up to it was already set up to connect. That's funny. All right, well, we're gonna watch it connect. So I'm also going to do an entire dedicated video using this modem to connect to any cell networks. I've used this cell network the cell modem to connect to private APN networks. I've used it to connect to public cell networks using a SIM card, and my own private networks as well. It's a great testing tool if you have like a SIM card and you want to see like, hey, does this SIM card get me internet, right? And you pop it in and you configure things the right way, and you can do that. I'm going to go over that whole process in another video, but right here I've got a script. It's using a certain configuration. One of the things that is in this configuration that has to be configured at the modem is that APN. It has to know that it is attempting to connect to the NMAT APN, and then the cell, those match up. So we are going to go ahead and we're going to run that. It's going to run some AT commands to configure the modem and do a bunch of stuff like disable that other antenna like I talked about. And a whole bunch of other stuff. But we can go over here and we can watch the connection happen. All right, so it says it got an IP address. Oh, that already happened right up here. Okay, awesome. So here you can see that we allocated the IP 10.8.0.3 to this host. Now, I believe I have this set. Okay, so now it's got 2 default gateways. So what we're going to do to force a ping packet through the LTE network here on our Raspberry Pi. So we successfully authenticated, are connected now from our cell modem, our user equipment, to our cell network using SRS RAN. And now we're going to send this ping packet over the network on the user equipment side, but we want to observe on our side of things here that traffic. And so here we can see this SRS underscore SPGW underscore SGI. This is that interface that we saw in the config file that it is going to tunnel the traffic out. This is where the traffic is going to egress out of the cell network onto our computer's network, and we have IP forwarding turned on. And so it will just forward the packets on according to my system's default routes, right? So if I go ahead and we start listening here, and then we are going to explicitly ping and tell the ping packet to take this path instead of this path. And there we go. We've got it. These packets are going over, are coming from our device here through our cell modem out over these UFL and SMA connectors, being decoded as LTE traffic, and is being forwarded using IP forwarding out to the real internet. And so this is a test bed that if I have an IoT device that has a UFL connector, I can tap in to that. I can put my own SIM card in it. And if there are not some extra checks going on in the software, I can see the traffic that's going across the wire over the LTE network. And so this was just, kind of just an initial look into the world of 4G LTE and using SRS RAN to host a 4G base station. I am planning on doing a few more videos where I dive into the SIM card programming and the operation of my user equipment, of that cell modem with a SIM card in it. And so definitely subscribe, and those videos will be coming out in a little bit. And hope you enjoyed this stuff. And I'm going to be doing more of this stuff, more technical deep dives into tooling that I use every day for pen testing. So thank you, and as always, have a great day.